In this video, I'm going to be walking you through the post lab for Lab 3 ideal gases. This is just one big giant data table with some calculations in there as well. The first thing on this data table is the mass of magnesium in grams that you measured out in the lab. So this is going to be some number that you obtained when you measured out your magnesium sample. And the first calculation that you're going to do is converting that grams of magnesium into moles of magnesium. This is just a straightforward gram to mole conversion. You're going to be using the atomic mass of magnesium. You'll just look that up on a periodic table. Then the next thing that you're going to do is calculate the theoretical yield of H2O. Now this one's kind of tricky because there isn't a balanced equation that's provided to you for this experiment, which means you've got to come up with it yourself. The reaction that you're doing in trial number 1 is the magnesium metal reacting with hydrochloric acid. And as you can tell from this question right here, one of the products of this reaction is H2 gas. The other product of this reaction is magnesium chloride, MgCl2. So this is the chemical equation for the reaction that's taking place that produces the H2 gas. This is unbalanced. And so there should be some stoichiometric coefficients out here. I'm just going to maybe put some question marks in there just to remind you that this is not a balanced equation. This just has your reactants and products. You need to balance the equation, and then what you're going to do is convert the moles of magnesium that you calculated right here in this box. I don't mean to point it at the grams, it's right there. Moles of magnesium, you're going to convert that into moles of H2 using the stoichiometric coefficients from the balanced equation. So whatever those coefficients end up being once you get this equation balanced. And then I'm going to, for trial number 2, the calculations are going to be all exactly the same. When it comes to this part, you have to rewrite the equation using acetic acid instead of HCl. Acetic acid's formula is CH3CO2H. But in terms of kind of correlating this to the magnesium and HCl equation, it's probably going to be easier if we think about acetic acid as HCH3CO2. So all I've done there is taken the hydrogen from the end of the formula and moved it to the beginning. And in this situation, the hydrogen in HCl is the same as the hydrogen in acetic acid, and the Cl portion of HCl is the same as this CH3CO2. So you'll be able to just kind of substitute this guy in this place, balance the equation accordingly, and you'll be able to answer this question. The next thing on our data table, the atmospheric pressure, that's going to be the pressure of the room that you obtained from the barometer, and it's in units of a millibar, which is standard unit of pressure for just an everyday household barometer, but it's not going to work in terms of science. You need to convert that millibar into units of torr. So this is going to be a millibar to torr conversion. Now you might be saying, oh my gosh, I don't think I've ever even heard of a millibar. Don't even try to look in your textbook to find that conversion factor because I'm pretty sure that it's not even in there. But don't even worry, Google can do this for you. So millibar to torr, look at that, MBARR. So the reason that I've written it out over here, I've written it as MB, that's because that's the unit that comes up on the barometer in lab, but the actual unit is millibar, and I think maybe I put too many R's on there. Millibar to torr, and we may even be able to get, oh yeah, thanks to Google, we can just have this automatic little converter pops up. So we will be able to enter in whatever the pressure was in millibar. Let's say it was 600. It definitely wasn't 600. Google's going to convert that to torr for us. So rather than needing to come up with that conversion factor, we're just going to use the internet. Or maybe your calculator has this conversion factor as well. Oh, I put that in the wrong spot. My mistake. We'll squeeze it in right here. Use the internet. And let's also make a little note that the MB represents millibar, BAR. So next question, total pressure inside the collection tube. So in the lab procedure, if you were paying attention, you were adjusting that gas collection tube to a certain spot. Once the procedure told you once you got it to the certain spot, in that position, the atmospheric pressure would be the same as the pressure inside the tube. So whatever you calculated here for your atmospheric pressure, that's the pressure inside the tube. The water temperature is a number that you recorded in the experiment, so you've got that written down in degrees Celsius. And then it wants you to report the partial pressure of water at your temperature. The partial pressure of water is the pressure of the water vapor, and it's a temperature dependent number. That's also going to be something that you need to look up. You cannot calculate this, you need to look it up. You can look it up on the internet. That is also probably in your textbook. So we're just going to go partial pressure of water at whatever your temperature might be. Maybe it's 25 Celsius. That's one that's showing up there. And this is going to give us a data table. As you can see, it's a data table that's got a variety of temperatures on it. So you'll be able to find your temperature in units of Celsius and then correlate that to the partial pressure of water, which is in units of torr. Whatever your temperature might be, this particular table, wiredchemist.com, this has a lot of data points on it. So that one would be really useful. I'm going to get rid of that. And so this is something that we are going to look up on the internet or look up in a textbook. We need a data table for that. I also wrote that in the wrong spot right there. Now the partial pressure of H2O inside the gas collection tube, we're going to do this using Dalton's law. So the total pressure inside that gas collection tube comes from the partial pressure of the water and the partial pressure of the H2 gas. The total pressure we figured out right there, or we reported it right there. The partial pressure of water, we looked it up, and so we have everything we need to calculate the partial pressure of H2O. H2. Next, we're going to take that pressure of H2 and we are going to convert it from units of torr into units of atmospheres. Conversion factor for that is in your notes, in your textbook. That's a very common conversion. So we're just doing a unit conversion there. Now we need to report the water temperature in units of Kelvin. We have the water temperature in Celsius. We're just going to turn it into Kelvin. The water temperature in Celsius. We recorded that in the lab. Volume of gas in the collection tube, you reported this in the data collection process. It is possible, I don't remember off the top of my head, that gas collection tube might be reporting in units of milliliters, in which case you would need to convert it to liters. So I'm just kind of putting a question mark there. Make sure you're reporting this in units of liters. Now it wants you to report the actual yield of H2O. Remember, the actual yield is a number that is measured. It's not a number that can be calculated, although we kind of are going to have to calculate it in this case, but this is going to come from actual data. It's actually going to come from the gas law. We want to calculate the moles of H2, and that is going to come from PV equals nRT, pressure times volume over the gas constant times the temperature. And this specifically is going to be the pressure, the volume, and the temperature of H2. So that means we want to report the partial pressure of the H2. We've got a lot of pressures on here. We've got the pressure of H2, the pressure of water, and the total pressure. We want to make sure that we're using the right one. The volume of any gas is it's the volume of its container, so we'll use whatever this volume is. And then you've got your temperature in Kelvin right here, and you're going to calculate N using the ideal gas law. And then last but not least, we're going to report the the percent yield of H2. The percent yield of H2 is our actual divided by our theoretical multiplied by 100. We just calculated the actual yield, and the theoretical yield we calculated way up at the very beginning. So that's going to get you through this. That's all that you have to do. I say it like it's easy. There's a lot of calculations here, but this is all that you have to do. Then you're going to repeat it again with acetic acid. You will not see exactly the same results because these are two different acids. They react a little bit differently. But regardless of how you do it, your results should be logical all the way through.